Okay, so fine, let's start. So in the last class, we had seen sets, and these are sets. They are we were we discussed that Python has an inbuilt uh, uh, function or inbuilt structure for set, where you can do operations, set operations like union, and we have, I think, listed also some of these operations, intersection, difference, etc. And this link is there where you can read in detail. Then we discussed about what are spanning trees and how to find minimum spanning tree, and we discussed about Kruskal's algorithm, and we saw how we can implement it using data structures, basically using Python. So here, the operations that you need, yeah, actually I was just going through it. Somebody asked this question after the class that when we do this algorithm, so we have to find out which entries belong, which nodes or which vertices belong to the same set. And we also do a merging, basically when two different sets become one set. So for this whole thing, we need both the operations, vertex to set as well as set to vertex, to be able to efficiently do it. We can do it inefficiently with a larger computational complexity, but to make it quick in constant time, basically, so we can maintain these two uh, dictionaries. Okay, so today's topic is binary search tree. We had seen binary search tree in previous lectures, I think, in when we were discussing about trees. Just quick recap of what we had discussed that time. So we saw binary search tree is a tree. It's a binary tree. Binary means every node has two children, or two or less, right? Two, one, or zero. That is the meaning of binary tree. Now, what is the meaning of binary search tree? It means it satisfies a property. That property is called binary search tree invariant. Just like you remember, you have heap invariant, right? So that was also a tree, but satisfied. Pardon? Okay. So the heap invariant satisfied a property that it was like a heap, right? The parents are larger or smaller than the children, right? So similarly, binary search tree follows a property, which is that the left subtree has smaller elements and the right subtree has larger elements. That's it. So let us look at this example. Now consider this root node. What is the left subtree? This is the left subtree. All the elements are smaller than 5. The root node is 5, and its left subtree has all the elements which are smaller than 5, right? And similarly, look at the right subtree now. All the elements are larger than 5. Okay, so it depends on us how we define the tree. You can say equal nodes are allowed or not allowed. Like, let's say equal nodes, if you're allowing nodes with the same value, then 5 could be here or here. But in, I think, what we are discussing, we are not allowing equal nodes. So basically, in a tree, two nodes cannot have same value in this convention. But of course, you can define it in different way also, where you allow same values. Okay, so is this point clear? That okay, it's a very simple concept. Binary search tree. Basically, we have a binary tree which follows this BST invariant, or this BST property, that the left subtree has got smaller nodes, or every entry is smaller than the root node, and the right subtree has got larger entries. Okay, now if you do an in order traversal of this tree, it will be ordered. Okay, so what is in order traversal? Quickly. Okay, I don't remember. Okay, I don't know if we have it here or not. So what is in order traversal? Just a recap. So in order traversal means you do the first in order of First do in order of the left subtree, then you process the middle node or the process, let's say you're just printing the value. And then you do in order of the right subtree. Right? So this is our, okay. This is our in order traversal. So how will the in order traversal for this tree look like? So first you will do the in order of, let's say in order of 5. So you will do in order of this subtree basically, and then the in order of this subtree, in order of this subtree, which is nothing. So you do the print of this node, you will print 1, comma. Then, okay, I think uh, we can maintain a stack also. So you do in order of 5, basically first you have 5, so go to the left subtree, put it on the stack. I am maintaining one stack here. Put 5 on stack, you are here now. When you are here, you have to go to the left subtree first. It's left subtree, so you will go to this tree, put it on the stack, and then you are here. Now it has no left subtree, so you will process this node 1, and now you go back to whatever was in the stack. 2 was in the stack, so 2 goes away, and you are here now. Now you have to process this. So basically 2 comes here, right? And then you go to the right subtree. So which means you go to 3. So you again put 2 on stack, go to 3, and 3 has no left subtree, so process 3. Okay, 3 has come now. Go back to 2. Now you are again at 2. Okay, now this whole thing is done. Now you have to go back to the root node 5. Now left subtree is done. You are at 5. Now you have to process 5. Okay, you process 5. 5 came here. Okay, now you have to go to the right subtree. So you go to the right subtree, put 5 on stack, leave 5 on the stack, and go to the right subtree is 6. Now you have to process the left subtree. Left subtree is none. So now you process this node. It's print this node 6, right? Then you go to the, then you have to process the right subtree. So you put 6 on the stack. Go to the right subtree. You are at 8 now. Now at 8, you will go to the left subtree. So put 8 on the stack. Go to the left subtree. You are here now. It has no subtree, so you just process this one. You print node value 7, and then you can go back to 8. So take it out, take it off from the stack, and you are at 8 now. You have to, now left subtree is already done, so you have to process this one now, or you print the value 8. And now you have to go to the right subtree. So leave 8 on the stack, go to the right subtree, go to 10. Means you print the value 10. That's it. And then you come out of 10, come out to 8, basically take off 8 from the stack, and you are at 8 now. Now this is already done, right subtree also is done. So go back to the, take out the next one from the stack, which is 6. You are here. And but this is also right subtree is done. So this is done. Now go to the previous one from the stack. Now you pop out this, and you are here now, and this is also done. So your whole process is over. So basically what you find is your in-order traversal is a ordered, it has got ordered values. So this is the property of binary search tree, that in-order traversal is ordered. Okay, I think, is it clear? Anybody has any questions here? Or else I'll move on to the next part. This we discussed in the previous class. I'm just repeating it for revision. So in today's class, we will be focusing on tree traversals. Just like we now saw in our traversal, we'll be extensively discussing traversals in today's class. Okay. Now, we saw what are the advantages of BST. Advantages are the insertion, deletion, search operations are very fast. On average, they take order of log n. Um, so the complexity is of the order of log n, which is very good. Of course, this is a bad example where if you have this kind of a tree, it is as good as having a linear structure. So the complexity is order n. So this tree is not good. I will discuss how to avoid such trees in the coming slides. Okay, now let's see some of these operations. We just now saw that okay, these operations, insertion, deletion, search, etc., are very fast. But let's see how do we do these operations so that you can appreciate how they are fast. Okay. So okay, inserting an element. How do we insert an element in a tree or in a BST in an efficient way? Okay, you know a BST means you have got everything following that property. So if you want to insert an element, you start from the root node. Then if the element is less than the node, which means that the element should go to the left subtree. If the element is larger than the node, this means that the element should go to the right subtree, right? You accordingly, you recurse or you move on to that subtree and keep doing it basically until you reach a null node. And wherever you find a null node, you create a new node there with that element as the value, right? I will be discussing in more detail. Okay, let us do this example. This will make things much clearer. So first of all, there is an empty tree. You have nothing. How do you insert 8? So basically, it's the root is empty. So you make a node or a root node 8. This is my BST. Is this a BST? Yes, it is a BST because it is following the BST invariant property. It is the only element, so nothing bigger or larger. So we can assume it is following BST property. Okay, now insert 3. How do we insert 3? So in BST, the 3 should be towards the left, right? So what you do is start from the root node. Since the element is smaller than this, so it should go to the left subtree. Okay, you move on to this one. So, but this node is null, nothing is there. So you just create a new node and add this element there, 3. Okay, this is done. This is a BST. Now go to the next operation, insert 20. How do you insert 20 now? So you will start from the root node. It is larger than 8, means my element 20 is larger than the root node. So go to the right subtree. There is no right subtree, no right node. You create a new node. So I created a new node 20. Okay, so this is a BST. Yes, you can see everything is ordered. Now insert 11. The next operation is insert 11. How do you do that? You will start from the root node. 11 is larger than 8. So go to the right node, right child. And here 20. 11 is smaller than 20. So go to the left child. So you will go here and left child is nothing. So you create a new node and insert 11 there. Okay. Now next operation is insert 5. How do you insert 5? Start from the root node. It is 5 is smaller than the root node. So go to the left child. 3. 5 is larger than 3. So go to the right child. There is no right child. So create a right subtree, right node, right child 5. Now insert 1. How do we insert 1? I have to go to the 1 is less than 8. So let's go to the left child. 1 is less than 3 also. So here you can create a node. Now insert 4. You are here. 4 is less than this. Go to the left one. 4 is larger than this. Go to the right one. 4 is smaller than 5. So go to the left one. So here you have to create a node. Right? Anybody has any doubts here? I think this was a very simple process. So you can see how inserting a new node is of order n, because you don't have to compare with every element, right? You're only comparing with the uh, uh, with next to next node, basically, which is of the order of log n. Okay, this was the solution. So okay, now okay, balanced BST. Now let us see an example where our what do you say, our uh, tree, our BST is in such a bad shape that it is not giving us any speed ups in our computations. Basically, let us see insertion operation. Insert one. So we don't have any root node here. So we create a new node, root node one. Then it says insert two. Okay. Compare with the root node. Go to the right one. The right subtree or right child is not existing. So create a new right child two. Now insert three. Start from root. It is three is larger than one. Go to right child. Three is larger than two. Go to the right child. There is no right child. Create a new node three. Now four. Go to the root node. Larger. Go to here. Larger. Larger. So you can see every operation is of the order of log n, not log n, but n. So it's a very bad BST. Although we are inserting elements, but it is not giving us any speed ups, right? So BST insertion becomes very bad for the ordered, if you're inserting ordered data. So that is why there is a need, if we kind of rearrange this tree so that it is balanced. Balanced means right subtree and left subtree, they have similar number of nodes or same number of nodes or similar number of nodes. Let us say if this is the tree, if I have to do an insert five next element, if I have this one, sorry, not one, let us say two, one, is this a BST? So two, left subtree has all smaller elements, right subtree has larger elements. Four, left subtree has smaller elements. So this is a balanced. This is a binary search tree, a BST. And now if I have to insert five, then you will come here, go to here, go to here, and that's with just two comparisons. After that, you are able to insert five here, right? So here you would have to you would have to do four comparisons. Here you have done just two comparisons. So this is a good tree. So basically that is the advantage of balanced binary subtree. So uh, now the question is, how do you convert any tree into a balanced search tree? Into a balanced search tree. How do you do that? So this is a assignment problem for you. Okay, is like you can do it on your own. I will come to this question later when I do tree traversals. There I will discuss the methods which you can use to create a balanced BST given any BST. Okay. Now the next operation is search for an element. Let's say you are given a BST now and I ask you, does it contain this particular element? Let us say in the previous BST, if I ask you, does it contain 4? So what will you do? In general, if you have everything unstructured, you have to compare every element and find out whether it has 4. But here it is faster, right? Because you know, if your value is larger than this, you go in that direction. Okay, so what do you do? Start from the root node. If the node is null, then the element is not in BST. But if the node is equal to the element, then you found the element. But if the node is less than the element, then go to the right subtree and search there. Go to the right child basically. And then if the node is greater than the element, then you go to the left subtree and search there. Again, the same process, right? So start from here. If it is, I think we have done already, just like you start, let's say you have to search 5, start from the root node, 5 is larger than 2, go to the right subtree. This one, 4, 5 is larger than 4, go to the right subtree, 5, and you found 5, right? Okay, so let us say in this example, search 11. So how will you do that? First, you will compare with 8, and it is 11 is larger than 8. Go to the right subtree. 20. 11 is less than 20, so go to the left subtree, and you found 11, right? You found 11 here. Okay, now search is clear. This is a very quick operation, order login. Now, next operation, removing an element. So removing an element means removing any general element. Basically, uh, I ask you, if this element is there in the BST, then remove it. Like, let's say if 11 is there in the BST, then remove it. So first you have to search for that element, and then replace that element with its successor to maintain the BST invariant. I will explain this line in next coming slides. So removing an element is not one shot process. You have to do little bit of a clever trick to be able to do it efficiently. So first, search for the element is simple. You have already seen it. Next is, you when you remove an element, then your binary tree structure is gone. Now you have to restore the binary tree structure. Plus, you have to also restore the BST invariant. The BST invariant, the BST property has to also be kept intact. So you have to do some clever trick. Okay, so that's why whenever we get an operation which is little difficult to understand, okay, break it down. What are the possibilities? In this case, what are the possibilities? The node could the node to remove, like for example, we have found a node. Okay, I want to remove this node. Let us consider a tree. I'm not giving the values, just some binary tree is there. And somebody asks me, can you remove this particular node? Let's say this is the value which I'm looking for. I'm going to remove this. If I remove this, then my tree BST property will be lost. I have to restore the binary tree structure so that my BST property is also maintained. Okay, so how will I do that? Okay, now I've split into these four cases are possible. Case one, let us say, case one is that when the node to be removed is a leaf node, right? So this is case one. And this is this node or this node, right? Both are case one. This is this node or this node or this node, this node. They are all case one, right? Because you have got only, let me do some color coding. Let's say my case one is green colored. So which nodes belong to case one? Can somebody tell me? Oh, let me name the node so that you can also A, B, C, D, E, F, G, H, I, J, K, L. Okay, tell me which nodes belong to case one. Which nodes belong to case one? Okay, so F, okay, okay, I'm reading the first answer. F, G, yes, H, K, L, and J, okay, K, L, and J, okay. And case two, they have only right subtree and no left subtree. They have only right subtree. Do we have any such node which has only, okay, none? Good. We have no such case. Let me write with this color. No such case. Tell me third case which has only left subtree. Let me write with yellow. Okay, E. I think everybody is getting it. So good to see that you are with me. Next is which has got both the left and right subtrees. Just draw it with blue, light blue. Which has got both left and right subtrees. A, B, C, D, I. Okay. A has got both subtrees. B has got, C has got, and D has got. Good. Yeah. Did we? Okay. I. We missed I. Okay. I think we covered all the nodes now. So you can see every node belongs to one of these four cases. Okay. Now let's see all these cases one by one. Case one, when our element to be removed is a leaf node. Okay, so what do we do if my element to be removed is a leaf node? Simply remove the node. That's it. No successor. It has no successor. So if you simply remove it, the BST property is anyways maintained. So simply remove that node. So for example, in this example, if you have to remove 4, what will you do? Remove 4, just remove it. That's it. You just remove it. Done. Uh, so the remaining whatever is left is still a BST. It follows the BST property, right? So this was simple. Case one was simple. Let's come to case two now. Actually, it is seen that case two and case three are equivalent. They are means they are same process has to be followed. So in case of case two or case three, so since we have only one subtree, just put that subtree there. Basically, the root node of that subtree is the successor. So just put that successor in the place of the node which is removed. So let us see some example now. Let me duplicate this slide. Okay, duplicate. Okay, let us do it here itself. Okay, tell me remove 5. If you have to remove 5 from this tree, what will you do? Okay, let's go to this one. Okay, if you have to remove 5, what will you do? So you have only one left subtree is here. The root of this subtree moves here. Basically, my 5 goes away. This 5 goes away, and this 4, this root moves here. So what we get finally is, okay, I will not draw the complete thing. I will just draw this, that we have 3, it has 1, and here it will be 4. Everything else remains same, right? So this is how it will look like. Now tell me, remove 30. Yeah, let me go to the next slide. Remove 30. If you have to remove 30, what will happen? So this 30 has to be removed. So this one goes away, and this one simply can move here. So basically you get 20 followed by 35 followed by 33 and 39. And 20 has other, and here also something that is all right. Okay, so can you see it? It is simply that you have put this node in place of the node which was removed. It was very simple, right? This is how we remove the element when we have only left subtree or only right subtree. Now, fourth case is when both the subtrees are present, then this becomes a little tricky. So it's not tricky, actually, it is very simple even now. So the successor could be either the largest value of left subtree. Okay, let us consider this case first. The successor is the largest value of the left subtree. The largest value of left sub. Let's say I want to remove 3. Let's say 20. Let's say 20. I want to remove 20. Go to the largest value of left subtree, right? If you want to maintain the BST, what does that mean? It means if I'm picking a value from the left subtree, it should be the largest value, so that the property that every other value is smaller than that value is followed, right? If you want to move um, out of this set, the set has four values: 10, 9, 11, and 15. If you want to make some element as the parent, then it should be the largest value, right? Because everything else should be smaller than that. So only 15 is qualified to come here. So I will take this element 15, and so if in case of remove 20, 20 goes away and 15 comes here. Okay, 15 comes here. And since 15 has got no children, 15 has got no children, so nothing, no problem. 15 has got no children, so no problem. If 15 had some child, then what would have happened? 15 goes away, that moves here. So it is invariably, it will be the case that when you are removing this node, this new node 15 will be either in case 1, like in this case it is case 1, or case 2, or case 3. It can never happen that this is also case 4, because if that is the case, then this is not the largest value, right? Then if it has a right subchild, a right child, and that right child is the largest value. So it will never happen that the case 4 repeats. It will be, you can have a left subchild, left child, and then that child will simply move here as we handled case 2 and 3. Okay, so basically this was simple. You find the largest value of left subtree and just remove it from there and put it here. Okay, the next possibility could be you go to the right subtree and take the smallest value from the right subtree. Like in this case, what is the smallest value of right subtree? It will be 30, right? So go to right and then go to left, 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 left. But here there is no left. So this is the value which can move here. And now 30 is gone, then what happens? 35 moves here, right? When 30 moves to this point, then 35 will move to the place of 30, and the whole subtree will move basically here, as we did in case number 2 and 3. Okay, so this was simple. Okay, is this point clear? Let me now make it a little more complicated. Let us say we had another element 25 here, and 25 had another right tree 26 here. Now what will you do? Let's say 15 also had here, 17 had left subtree, left child, 16. Now tell me, how will you remove 20? If I remove 20, then what will come? So, okay, both these possibilities are valid. So you can do either of these, right? When you are removing 20, either take the largest value from left subtree, that is a valid way, or you take the smallest value of the right subtree, that is also an equally valid way. Okay, now tell me in this tree, if you want to remove 20, then from the left subtree, how will you do it? What will come here? What will come here? 17 will come, yes. So how will you do it? So go to the left subtree and then start moving right, 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 right until you get no more right. So go to the right subchild, go to the right subchild, go to the right sub. There is no right subchild, so this is the final destination. So this 17 will move here. Now when 17 moves there, what happens to 16? When you are removing 17, basically you are removing 17 from here, right? That is case number 3 or 2 or 3. This means now it has only one successor, that successor will occupy this position. So 16 will move here. And if whatever subtree was there attached to 16, that will as it is move here. Let's say if 16 had other subtree attached to it, in this case it is not possible because 15 is already consumed. I cannot have anything, maybe 15.5 something, 15 and a half. and here 16 and a half. Then those things will straight away move here, means along with 16. Okay, so how will the final tree look like in that case? So it will look like we have 8. Let me draw it with yellow only. You have 8, and here you got 17. Here you got 11. Here you got 15. 9, 10, 15, and 17 is already gone, so 16, and whatever the two children of 16, 15 and a half and 16 and a half. Pardon. Instead of 16, if it was 14, okay. Tell me, somebody can tell me the answer. If it were not 16 but 14, what would have happened?
So the binary search tree variant invariant would not have been satisfied in the first place itself.
Yeah, yes. Because we have this, if this were 14, then, if this were 14, then the right subtree of 15 cannot have a smaller value than 15, right? So every value here has to be larger than 15. So 14 is not possible. Okay, good. Okay, let us give it a closure. That is it. I think remaining rest, everything remains same. This is 30 and the other things are same, right? These things are same. Okay. And now tell me, how will the other thing look like? If I, instead of moving 17, if I go to the right subtree and find something from right subtree, then which entry will come? In the right subtree, 25. Very good. So go to the right subtree and then do left, 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 left until you reach the place where there is no further left. So in this case, 25. So 25 is the smallest value. Okay, take it to this position, and whatever is attached to it, it will simply move here, right? So what you will get is here 8. Okay, maybe I will try here 8. Oops. 8, and then here we got 25. Here we got 11, and everything else is same. And here we got what, 30, and the left child of 30 was 25 earlier, but now it becomes 26. And the right child is 35, and etc, etc. That remains same, right? So you can see the BST invariant property is maintained because you have taken the smallest value from the right subtree. Okay, so this is how we remove an element. Little bit tricky, but very clever. Okay, now we are going to move into our major topic today, that is tree traversal. How do we traverse the trees? You have already seen it in the previous lectures, but I'm just expanding it today. Okay, so tree traversal, most popular are, you have seen in order just now in the beginning of the class. Pre-order and level order are popular. They are also known by the names depth first search and breadth first search. They are possible for any graph in general, not just a BST or not just a tree, but any graph. Graph means when you have vertices which are connected via edges, right? Any structure basically. Tree is a structure, like there is a parent and child hierarchy is there. But if there is no hierarchy, any node can be connected to any other node, or any vertex can be have connection with any other vertex through an edge. That is a graph. It's a general framework. And to traverse a graph, you can do depth first search or breadth first search. What is depth first search? It is similar to what pre-order search in our tree traversal, and what is breadth first search is similar to level order traversal, which we will see now. Okay, let us do a quick revision of pre-order traversal or depth first search. Okay, so basically what does it mean? You go to the deepest point first, like from here, go to the deepest point to, okay, then from here, this is not a binary graph, this is just a any other graph. This is not a binary tree, it could be any tree in general. Then this is then you go to the next 3, 5, 8, like depth first. Go to the deepest point, and then come back and go to 9, and then go to 6, then go to 10, and then go to 4, then go to 7. Right? You can see that you are going deepest point and then coming back. But the okay, and but the breadth first search means you go to 1, then 2, 3, 4, then 5, 6, 7, then 8, 9, 10. So basically you are going layer by layer, or one step in all the directions, second step in all the directions, third step in all the directions, right there. But in depth first, just choose one direction, go to the end point, then come back. To the next direction, go to the end point, come back. Next direction, end point, come back. That is the depth first search. Okay, so let's do depth first search quickly, which is, you have seen this code before. Let us quickly do it for this one. How do you traverse this whole tree? Let us say you want to find some element, you do traversal, or you want to remove, yes, basically for search, right? How do you do pre-order traversal? This is the procedure. You first process the current node, and then process the left subtree, then right subtree. Basically pre-order of left subtree, then pre-order of the right subtree. Okay, if you want to process this node first, okay, start from 1, process this node, output is 1, right? Output is 1. Now go to the left subtree, or in this case, go to the first child, and go to the first child, then put 1 on stack, and go to the first child, and then process this child, you get 2, right? And then it has got no children, so okay, pull the entry from stack. So now, okay, then you take this one out from stack, and you are here now. Now go to the next child. Next child is 3. Put 1 on stack, and you are in 3 now. Now here again, go to the left subchild. So put 3 on stack, and you are here now. You're pointing to here. Your current node is this one. Now you are here. Now again, go to the left subchild, put this on the stack, and you go to 8. Now it has no subchild. So oh, we had to process also. I'm sorry. 1, 2, 3, 5. Before putting on the stack, you have to process it also, right? 3, 5. Okay. Now this one has no subchild, so 8. Okay. Now this has no subchild, so okay. Yeah, this part is finished. Take the next one from the stack. Okay, 5 is from the stack. Remove 5 from the stack, and you are here now. Now again, you have to go to the next child. So again, put 5 on stack. Go to the next child, which is 9. Now process 9, right? And 9 has got no children, so okay, so 9 is done. Now take the next entry from stacks. Next entry from stack is 5, so you are again at 5 now, and all the children are done. So okay, so go to the next entry from the stack, pop 3 from stack, 3, you're at 3 now. Now the next child of 3 is 6. So okay, again put 3 on the stack, and go to 6, and process 6. 6 is processed. Now go to the child of 6, put 6 on the stack, go to its child. Child is 10, process 10. And now 10 has got no children, so okay, this is done. Take the next one from stack, so 6 pops out. You are here. Then this is also done, no more children. Okay, take out 3 from stack. You are here. This is also done. Now take out 1 from stack. You are here. And now see, the next child of this is 4. So again, put 1 on stack. Go to the next child, which is 4. uh, and process 4, and then go to the next child, put 4 on stack. 4 as one child, 7, process 7, and this is done. So okay, now take out the pop out 4 from the stack. You are at 4 now. Now pop out, this is also done. Forward 1 from stack. You are here now, and this is also done. So you are done with it. Your algorithm means your traversal is complete. So you got 1, 2, then 3, 5, 8, then 9, then 6, 10, then 4, 7, right? This is the pre-order traversal or depth first search. Okay.
Sir,
Pardon?
are we not talking about binary trees anymore? At least for general graphs,
Yeah,
because one. Oh, okay.
yeah, this is general tree. This basically, when I'm saying tree traversal, this is valid for trees.
Yeah.
When I say depth first search is the same process, but it is valid for any graph, any connected vertices. It could be, they could be cyclic also. No restriction.
Yeah.
Okay.
Thanks.
Okay, I think, yeah, I should specify here that, let me, since this point has been raised. Oops. Okay. Tree traversal. Maybe I'll. Why it is not cutting it down? Okay. Okay. Just. Okay. Some message. Okay. So this was a pre-order traversal or depth first search.
So where do you upload the slides? Is it there on your website, or is
I,
there? I
I will.
couldn't find it on Mookit.
Yeah, I will upload it. I will upload it. I have not done it yet. Yeah.
Okay,
Okay.
sir. Okay.
Yeah. Next is level order traversal or breadth first search. Okay. So this traversal is step by step. You take one step in all directions, take next step in all possible directions, take next step in all possible directions. So like breadth wise, you are moving, right? So output will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. But how do you do it algorithmically? I will discuss in the coming slides. Basically, you do it with the help of a queue. So you make a queue. Your queue, you remember, your queue is uh, uh, first in, last in, first out. Right? No, first in, first out. Queue means you enter from. I'm sorry. You enter from one side and come out from the other side. You enter from one side, come out from the other side. Okay. So let us try it. So go to the root node. Go to the root node, and you. Did I not write the algorithm for this? Oh, okay. Okay, I have not written the algorithm. Anyways, so it is there in the coming slides. So what you do is you get the root node, you process this node first, and then put all its children into the queue. So 2 comes here, 3 comes here, 4 comes here. So everything has come in the queue. Now you take out the next entry from the queue. So you dequeue. So when you dequeue, your 2 is gone and you are at 2 now. So process 2 and put all the children of 2 in the queue. There are no children. Okay, no problem. So then take out the next entry from the queue, which is 3. So now 3 is dequeued, and now you are at 3. Now at 3, process 3, and put all the children of 3 in the queue. So basically, which are 5 comma 6, right? 5 comma 6. So they are fed into the queue and 3 is done. Now go to the pop out or the DQ the next entry from the queue, which is 4. So 4 is DQ'd now. You are at 4 now. Process 4 and put all the children of this in the queue. So which is 7. Okay, this is done. Now take out the next element from the queue, DQ5. Now 5 is here at 5 now. Write down all the children in the queue. Put all the children in the queue. 8 and 9 go to the queue. 8 comma 9. Right now, 5. Okay, it was to be processed also. Process 5. Now it is done. Now DQ the next element from the queue, which is 6. Okay, process 6 and put all the children in the queue, which is 10. Okay, so now 6 is done. Now go to the next element from the queue, which is 7. So DQ7 and put all the children, no children. Okay, nothing, no problem. Go to the next pop out, DQ next from the queue, which is 8. Process 8, put all its children, no children. Okay, fine. Then again pop DQ the next element, which is 9. Process 9, put all its children in the queue, no children. Then pop out the next 10. To process it and put all its children in the queue, no children. Okay. Now pop out the next element from the queue. Oh, the queue is empty. As soon as the queue is empty, that's it. You're done. So that is your level order traversal or breadth first search. Okay. So this is the algorithm, or this is the process. And then I will show you the exact code also a little later. Okay, this is the code. Okay, now I am trying to show you my implementation, which I did in Python. So I used a binary tree class. Why I used it? Because I wanted to make this pretty print. I wanted to print like this. I could have done it without this also, but then I will have to write a separate program to do the printing. So I didn't want to do that. So I just used an existing existing class. It's called node, and I call it as tree node. So tree node has got 4 variables: value, left, and right. Right? For a binary tree, what do you need? You need the current, what is the value, the data stored in here, who is the left child, who is the right child. That's it. And the right and left child are also of the type node only or tree node only. Right? And the value could be of any type, string or number. Right? Okay. Now, using this, I create a tree. How do I create a tree? I say tree is equal to, tree is initialized as a tree node 3. A new tree node is created. Basically 3 is created. Now I say tree dot left is 9. So basically the left node is a new the left child is a new node with the value 9, and right child is a new node with the value 20. And then again, tree dot left is 15, tree dot right. So this is the tree, right dot right is 7, basically new node 7, and then here 8, right? And then I do pretty print. This is printed. Now I create this class for my BFS search, breadth first search. So what I do is I will say, what do I need? I need a queue and I need the output value, right? If you remember your previous thing, you need a queue to store all these values, all the nodes, and you need the output value. You can either print it directly or you can save it in an array. In this case, I'm saving it in an array, and in another implementation, I will also print it. So that is not an issue. Only queue is important. For BFS, queue is important. Then you do level order traversal. How do you do level order traversal? Given a route, basically you start from there. You start from this node, right? Like if I say b dot level order, b is basically, as you remember, b is the BFS example, this class, an instance of this class. Then this tree is this node basically, right? So what you do is, first of all, pardon. Okay, so first you will put this node into the queue. Okay, I will do queue dot append. I'm using just a list as a queue, so I'm using very that dequeuing process. So queuing is easy, but dequeuing means you have to first read the value and then delete that node. So okay, because I'm implementing it with the list, which is very inefficient. Anyways, just for ease of understanding. Okay, so you put the root in the queue. Now you run an infinite loop. Basically, you say as long as your queue has any entry, you process that entry. So take out the entry from your queue and do this process, the BFS process, and then delete that entry. And then this process itself will update the queue also. That is why you can keep doing this over and over again as long as there is any entry in the queue. And what is this process? Basically, as I told you, and first of all, you process that node, then put the children into the queue. That's it. If you remember from here, process that node and put the children into the queue. So process that node, basically you are just saying your retvel array, you're just appending these values. You're processing the node. Right? And this is queue the children. That's it. So very simple algorithm, right? Okay, this is another way of doing it where I'm using, this is an inefficient way basically. I'm using a recursion. I'm calling the same function over and over again. So I'm saying first append the left child, append the right child, right? And then process this node. And then if my queue is empty, then return. If the queue is not empty, then you dequeue the next element, like next node or next root, and then repeat this process or recurse over this process. It's a recursive implementation. It is inefficient because you are maintaining a queue as well as a stack. Recursion means you are maintaining a stack also. So this is an inefficient process. So it will require more memory. You have to store queue as well as a stack. So, but anyways, the answer is same. Answer means the output is same. Okay, now I think with this we have done a significant thing. We have covered the tree traversal, which is a very important topic, especially for those of you who are doing machine learning. All of you are doing machine learning, so for you it is very important, very useful tool. How do you search for values in machine learning and AI? Whenever you have applications which require trees or graphs, and there are so many applications which require trees and graphs, so all these concepts will be very useful for you. Okay, now this is an exercise balancing a given BST. You have to write a code to given any BST. Like this was a BST, right? This was a binary search tree. This you can check it. It follows the properties of BST. So this was a BST. Given any BST, you have to balance it. Clearly, this is not balanced, right? How you can see it? You can see this root node has got, in the left subtree there is only one node. In the right subtree there are 4 nodes. This is an imbalanced BST. But how to convert this into a balanced BST? So I will leave it to you to solve. There are multiple ways. but I like one way, which is very efficient as well. So, okay, when you are designing an algorithm, take into account uh, one thing is that what is your complexity, computational complexity, the big O notation, right? What is your complexity? Try to keep it as small as possible. And second is, which is related basically, what is your speed of execution? Okay, so this is how you test your speed of execution. They are both related because the big O notation is basically when your data is very large, how does your speed scale? And so, but you can do a quick empirical test. Empirical means you take some data and do the testing by actually running the code, not a theoretical or not an analytical analysis, but uh, a real time or a real world, what do you say, a real run of the code. So you have, so you can import in Python the library called time, which will tell you the current time. And I will define a function which I want to test. How much is this an efficient function or not, or how much time does it take to execute? And I have to just call t start, then call that function, and then note down the t end, and the difference of t end minus t start, that is the total time taken by this function, execution of this function. Now, since it is possible that your function takes so less time that it is beyond the precision level, let us say 0.0000001 seconds, something like that, which is very small. So what you do is you repeat your execution a large number of times, let's say 10,000 times, 1 lakh times, so that this total time taken becomes a significant thing. Basically, the precision is large. I think you remember your physics experiments where you don't just rely on one reading, you run it multiple times, right? And let us say you want to measure I remember one experiment, you have, you want to measure the thickness of a paper, thickness of paper. What do? You take, let's say 100 papers, stack them together, measure their thickness, and then divide by 1,000. That is the thickness of single piece of paper. So why do you do that? You do that because your measuring instrument has uh, a smaller precision, or the precision is of the order of what you are measuring. So that's why you make it bigger, and then when you divide by the total number of pages, that you get higher precision. Okay, I think this was a simple physics example to illustrate this point. Now I want to give you some exercises for your own practice. So you can expect something similar in the quiz or exam. These are, this is a difficult, means, okay, this is not very easy to solve, but this will encourage you to think a bit that how do you approach these problems. Okay, so given a two-dimensional board, for example, this is a board containing X and O, capture all regions surrounded by X. So whatever is surrounded by X, you capture it. And a region is captured by flipping all the O's in that, all those O's into X's in that surrounded region. So basically whatever O's are in the surrounded region, just convert them into X. So for example, take this example. After running the function, the board should look like this. So basically, so here neighborhoods are only, the neighbors are only top down, left, right. The diagonal entries are not considered neighbors. So let us say this O, the neighbor is this one, this one, this one, this one. This is another O. The neighbor is this one, this one, this one, this one. And another O neighbor is this X, 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 and O. So basically you can see this entire region, these three nodes, they are completely surrounded by X. So they all will become X now. But this one, it is not surrounded by X at the bottom because it's at the corner. So it is not captured by X. Okay, so surrounded regions shouldn't be on the border, right? If they are on the border, if any O is on the border, they are not flipped. And any O that is not on the border and it is not connect to any other O on the border, that will be flipped into X. Two cells are connected if the adjacent cells two cells are connected, if the adjacent cells are connected either horizontally or vertically, basically up, top, down, or left, right. The diagonal entries are not neighbors. Very simple exercise. So how will you approach it? You basically, you have to find all the O's which are either on the border or they are connected with O's on the border. And connection means through O only. X is not a connection. So, okay, so what I will do here in this case, I will traverse the entire boundary. Whatever O's are there on the boundary, I will leave them. I will say these are the these are not captured, and whatever O's are connected to these O's, they are also not captured. For example, if I had this, if this were also an O, then nothing would have been converted, right? Everything would have stayed at O. This all would have been O. All would have stayed as O, because this is connected to this one and this one is connected to this one. This one is also connected. This one is also connected. So everything is connected to this O. So they would not have converted into X, right? So I hope this problem is clear. So how will you do it is, you will just first run through the border, and wherever you find an O, then you do a depth first search. Find if any of its neighbor has got, any of its neighbor is O. Okay, I got an O. Go to this one, any of its neighbor is O. Okay, I got this one and this one. Then you, since it is depth first search, you go to this one first, or you define your direction in whatever way possible. So go to the first one. Does it have any neighbor? Yes, this has the neighbor, which is, then go to this one. Okay, does it have any neighbor? Yes, this has another neighbor. Does it have any neighbor? This has a neighbor, but this is already converted. So, and no other neighbor is left. So we have covered all the O's. So basically you have covered all the O's. And then you come back, you remember you are in your stack. This was there. So when you go there, you find this is already already traversed. So you can stop your algorithm. Means you can you need not process this node any further. So come back to your stack, and in the stack nothing else was remaining. You are here, and then move on to the, if you find any other O. Okay, so means this is how you can approach this problem. Simple depth first search. I would encourage you that you write the code yourself and practice on this problem. Okay, another example of depth first search. Given an integer matrix, find the length of the longest increasing path. This is a matrix which is given to you. Find the length of the longest increasing path. So basically when you say path, it could be either left, right, or up, down. You cannot go diagonally, and you cannot go out of the boundary. You have to stay within this. For example, it is not a periodic thing that you, from 8, you jump onto this 6. That is not allowed. You, after 8, you cannot go to the right. Okay, so what is the longest increasing path? I will, if I start from this 1, 2, 6, 9, that's it. But if I go from 1, 8, then everything else is small, so nothing. So this one cannot, from starting from this one, you cannot find the longest increasing sequence you can find is only 1, 8, length 2. So go to this one from here, 1, 6, 9, 3, 1, 6, 8, 3, but 1, 2, 6, 9, 4, very good. So largest. Then go to 2, and like that when you cover. So here also you have to use depth first search. I think the idea is clear to you. So yeah, this is another exercise which you can do. Now coming back to our balanced binary tree, with this you can do with the breadth first search. Okay, now I leave it to you how you are using breadth first. Oh. No, I'm sorry, it is not breadth first. Here you have to do in order traversal. Here you can do in order traversal, right? Because you know, an in order traversal of any BST gives you the ordered list of nodes. And once you convert your tree into an array, an ordered array, then again convert it into a BST. So what is the complexity? The complexity will be of order n, because you traversal itself is order n, and then you convert it into a tree that is also order n. So complexity will be order n. Okay, so yeah, I think one point I missed when I was discussing this. When you are testing your code, two things are important. One is how much time do you require, complexity. Another is memory. How much memory do you require? If you are creating stacks and queues which are just occupying all the memory, it is not a very good algorithm. So you also have to consider that your algorithm should consume least amount of memory. So both time as well as memory, both are important. Okay, I think, yeah, if you go to, let's say, machine learning, you also have limitations on computational resources. For example, you are deploying your code on a mobile phone. It has got very low-end processor compared to your GPUs, etc. So you have to also consider that it should not be uh, the processing should not require that many resources. So basically it is covered in the time complexity itself, because when doing time complexity, you assume it is a single processor. But of course, in GPUs, you have multiple processors, so you can increase the speed accordingly. But yeah, but okay, these are the considerations we have when we write a code for machine learning. Uh, okay, so I think we can stop here. If anybody has any questions, please feel free to ask.
So how do we decide between DFS and BFS? Is there any way we can, any specific logic that we should keep in mind, or is it just that we should try out and see?
Um, no specific logic. Okay, so some you can compare their relative advantages and disadvantages. For example, if you're okay, let me give you an example. Let us say if it is an infinite tree, which method will you prefer?
Breadth first.
Yeah,
Breadth first bench.
yeah, because DFS will be just lost, right? If it goes in one wrong branch and it is lost forever, well, it's an infinite tree. So we prefer breadth first search, so that, and also if you have a rough idea how far is your solution, let us say if solution is nearby only, then no point of doing depth first, you do a breadth first only, right? And other considerations could be a BFS uses a queue while DFS is using a stack. So how big stacks or how big queues do you allow, right? Um, that is also another consideration. DFS means you go to the extreme end and your stack is completely filled, but BFS mean you are, yeah, I think, yeah, that is another consideration you can keep in mind. Yeah.
Sir, so can you please go back to the previous question, the question just before it? Yeah, in this question. So in this question, you are using DFS. So the time complexity is order n square here, right?
What is n?
Oh, sorry, n into m. That n is the number of rows and the m is the number of columns.
Okay.
So that is the case here, right?
Yes.
So I'm just asking that like when you're converting this O to the X, so you are doing that here in place, or you are just using extra memory? Because like if we are allowed to use some extra memory, then we can just do a simple traversal from first element to the last cell, and then just compare and just see its surrounding cells. So in that way, I don't know if I'm confusing this with some other question, but
Okay,
actually that is my doubt here.
so in this problem, we are not converting. We are only finding O's which should not be converted.
Okay.
Right? We are only finding O's which should not be converted. Everything else we convert. That is the strategy which I explained. But of course, you can also devise another strategy where you are converting. But that will be difficult, right? Because how do you know whether this O is not connected to any other end? Okay, so maybe you can think about it, but this is one strategy which I explained, that you find out what O's should not be converted and remaining
And
everything can be converted.
and so one more thing actually about the quizzes. So in the quizzes, do we expect some programming assignment type questions that we actually have to write some code,
Yes,
or it is just theoretical?
yeah, it will be programming assignments also, just like I can give you this same code. I will say, write this code, right? I've already discussed the solution in the class, or I've already given you as an exercise. I can ask it in the quiz or exam, but I can also ask similar problem in the quiz or exam.
Okay, sir.
Yeah.
Thanks, sir.
Thank you. Yes, there will be coding component as well as theory component, because this data structures algorithms part, I don't think we will have any theory questions. Mostly it will be coding questions only. Okay, thank you. I will let you know the quiz dates very soon, but I will do it. Okay.
So
So
even if the videos takes time to upload, if you can upload these